Okay, thanks. All right. Sorry, I'm not used to switching up the share. Okay, so here we go, whiteboard. Okay, so let's say we have a child and then it's got two parents. It doesn't matter the genders involved, you know, it's really like arbitrary. And then these are the grandparents from that particular parent. I got to move stuff around here. And then sorry, that doesn't make sense. That should be, I drew that wrong.
Okay.
Let me just start again. Now I lost my controls. Okay, so here's the child and it has a pair of parents. Okay. And each of its parents have a pair of parents. So it's got 4 grandparents. And I'm going to get really small here. So you have a person has 8 great grandparents. Okay, I'm going to grab another color and just make like, I'm just going to thicken up these lines so that it's like the examples in the lecture. Okay, so the question is, oops. Okay, sorry, those aren't okay. How related is baby to great grandpa, this particular great grandpa?
So in this case, if we're just looking at that great grandpa, would there be 3 lines of descent? Like, are those what the, okay.
Yep.
And could we just do 0.5 to the power of 3?
Exactly.
Oh, okay, awesome.
Exactly. Yeah.
Okay, cool.
Yeah. 0 point. So we just have one term in our sum, and our this symbol is supposed to be for to the power of 3. Yeah. So
Okay.
it would be, it's like 0.125 maybe.
Oh, I don't have my calculator.
I know.
I'm gonna trust you.
Yeah. Yeah, I think it's 0.125. Yeah. So you are you get 12%, or you share 12.5% of your genetic variation with any one great grandparent.
Oh, okay. Okay, yeah, that makes sense.
Yeah.
And then if we just kind of like keep going up, we just increase that exponent, I'm assuming.
Exactly.
Okay.
So your great grandparent, it would be 0.5 to the power of 4. And so so you're only like 6%, 6.25% related to your great
Okay.
grandparent.
Okay, yeah, that makes sense.
Yeah.
And my last question regarding those was just question 5 from the lecture slides, where it was like the dad had mates with 2 sisters.
Okay. Yeah, so this is one of these ones that's like annoyingly complicated. Okay. So right, okay, so there's these 2 children, A and B, and this is unusual. So I don't think you wouldn't be able to like Google the answer to this one. Whereas if you just Googled like, you know, grandparent, grandchild relationship, things like that, you'll find the answer to that online. Okay, so in this case, you want to know how many ancestors do these 2 young children share. Well, they have the same dad. That's one of their shared ancestors. They don't have the same mom.
Okay, yeah,
But
that was confusing me because I was gonna ask why the moms aren't a part of it, but now that so they're not, so if they don't share like the same parents, then that wouldn't be a common ancestor.
right, well, they don't have the same mom, but their moms are related to each
Yeah,
other. So they actually share
the grandparents.
a grandpa and a grandma
Okay,
through their moms.
okay,
So they're like both siblings and cousins.
yeah.
Yeah. So that's why it's like an unusual one. Um, but okay, so you can't get to like the topmost shared ancestor for over on the mom's side, or the non-dad side, I guess, it is like grandpa and grandma on here. So your three terms here come from like dad, grandparent one, and grandparent two. And then to get the powers here, to get to dad, or get from B to A through dad, it's just the two steps, right? As any kind of sibling relationship would be.
Oh, okay, and then so like from B to A, it's two, and then if we wanted to go to B's mom, for example, it would be B. Is that where the four comes from?
The four comes from, so we're actually focusing on like this
Okay.
ancestor and this ancestor. So we have to go like one step, two step, three step, four step. And then we also, so that's where that four comes from. And then if we're looking now at G2, it's one step, two step, three step, four step.
So the thicker black lines pretty much.
Yeah, exactly.
Okay.
The pink lines are just showing the matings. It's the thick black
Yeah.
lines that show whenever like there's a like meiosis and descent. So the thick black lines are the thing that gets used to calculate these exponents. Oh yeah, Charlotte, you had your hand up.
Yeah, so I'm sorry, I'm just confused about the relationship between A and B. So they share the both sets of grandparents, but they have different moms?
Correct. So
Because okay.
yeah, so they also have a shared pair of grandparents through
Yeah.
dad, but because they are descended from dad immediately, we don't have to also add terms for those other grandparents
Hmm.
because they have the same dad. It's hard for me to explain that, but because they both, we know exactly how they related they are through dad. So we don't,
Okay.
we'd be adding extra relatedness if we then went into dad's ancestors. Like they share
Right.
all of dad's ancestors, they share.
So even though their moms are related, their moms aren't common ancestors because they come from different moms.
Well, yeah, exactly. So
Okay. Okay.
you have to find like the kind of top of the tree,
Right.
but we don't go any further than that, like which is why
Yeah,
sorry.
I was just gonna ask, so like say they didn't share common grandparents, but they did share common like great grandparents for some reason. If that's even possible, you wouldn't ever go up that far in a tree, would you? Or would that count for
Yeah, with that we would. Yeah.
oh,
Yes.
okay.
So
Okay.
like I mean, I'm not going to give you really complicated ones. It is on the midterm, but I'm not going to make you do these like unusual ones. But I'll try a whiteboard example of what I think you're asking again.
Sorry, I didn't mean to hijack Janessa's question. I
No,
just
no,
was
it's okay.
confused about why they weren't related.
I think
It's
it's
all right.
helping. I think it's helping. Okay. So sorry, it's like tricky to draw on the fly. This is why I wish I had a real whiteboard.
I also just wanted to ask in terms of formatting for this kind of question on the midterm, would we be drawing out the tree and showing it, or would we just be giving like the numerical answer?
um, like in principle, I could give you a question where you have to draw the tree.
Okay.
Um, there isn't a tree drawing question on this midterm, but there it is kind of figuring out some relatedness is on it.
Okay. So we'd be likely drawing the tree anyways for ourselves just to or like we'd be figuring out the tree if it was provided or drawing
Exactly.
it out if it was okay.
Exactly.
Perfect. Thank you.
Okay. So what should I, so you want to, okay. So yeah, oops, I don't want to use black. go with blue. Okay, so like parents, grandparents. I'm just going to use this for the like pairings, and then I'm going to go to black and thick lines for these examples. Oh wait, I wanted to show like great grandparents. Sorry, I'm not very good at this. Okay, so let's think about your like um oops, want that to be thicker. Oops. Okay, I don't even know what the relationship is between these. This is like some kind of second cousin, right? Like this is a relative, but a pretty distant one. This is your great grandparents. This is the sibling of your grandpa. So how related are you to the sibling of your grandpa?
Would that make it like a great aunt or a great uncle in that case?
Maybe, yeah.
Okay.
You sound like more confident about it than me. Yeah.
I have no idea, but I
Yeah.
think that's right.
Yeah. So, okay, so it's not a direct descent relationship because B is not like B is not directly descended from A and vice versa. So how many common ancestors do B and A share?
Would it be
Would
2?
Exactly. Exactly. So they share these two, like, and we don't need to go any further. Of course, they share like more ancestors above these two, but these are their two kind of direct shared ancestors.
And then from what I'm gathering, it would be 0.5 plus 0.5 plus 0.5 plus 0.5, all to the power of 2, because there's 4 black lines to get to A. Or
Okay.
am I mixing them up?
Okay, so we're going to add up two things. So we're going to have like sum, or like R equals the sum of let's call it like big R1 plus big R2. Okay. And to get big R1, it's going to be 0.5 to the power of something, and then it's going to be 0.5 to the power of something. Okay, so we want to figure out, so we've got two ancestors, so we've got these two numbers to add together.
So in the questions, sorry, just to clarify, if in the question, like the number of units of 0.5 that you're measuring are the number of like directly common ancestors they have, and not the number of like things we're trying to figure out the relatedness of, right? Like it's 2 because it's grandma and grandpa, not 2 because it's A and B, right?
Correct. It's always,
Okay.
it's, yeah. R is in this course, we're only talking about R as a relationship between two individuals. So there's always, it's always A and B or whatever. But
Okay.
to get R for A to B, we add up terms, and the number of terms we add up is just equal to the number of those kind of top of the tree ancestors they share.
Okay.
And so they're not direct descendants. So we have to figure out, okay, they just share these two, you know, these are B's great grandparents and these are A's parents. And those are their shared two ancestors. And so for R1, we just figure out what's the exponent of X for R1. Well, it's just the number of block paths it takes to get from A to B,
Oh.
B to A.
Okay, so for the 0.5s, it's the number of shared descents, not the amount of black lines it connects, right? Because I think I accidentally flipped my numbers and said 0.5 like 4 times.
Yeah, I think you did.
Okay, okay, so I think it would be 0.5 to the power of 4
Yeah, exactly.
plus another 0.5 to the power of 4 because there's 4 lines that need to get from B to A.
Exactly.
Okay.
Exactly. And I don't know what that is off the top of my head. I guess it's like I just have to use my computer to calculate it, or my phone.
So there would never be a question, or would there be a question, I guess, where the relatedness between the two people to their related ancestor would matter, or are we strictly considering the relatedness of the two like given people?
So do you mean a situation where we're talking about 3 people?
I mean, that is a question I have, but in this case, like A is a lot more related to the ancestors than B is, but that's not a factor we have to consider in this kind of question, right?
No, yeah, but you might have a question. So where this is applied in this course is when we look at Hamilton's rule. And so Hamilton's rule can involve these inequalities where we say like, who, if you have to choose between caring for this relative or this relative, or like who will you like, who does Hamilton's rule predict you should provide most care for? And you might be considering like more than one possibility.
Right.
Like, should
'Cause
I,
I mean,
oh, go
oh,
ahead.
sorry.
No,
I just was gonna say, like in this case, the two grandparents that are the related, they'd be more inclined to care for A since that's their immediate offspring, right?
yeah, exactly. Yeah. So these two, like let's just look at one of them at a time. I'm just gonna put some text on it. Okay, so like I can't move it once I type the text. So G here, we can talk about how related is G to A, and we can talk about how related is G to B. So G's relatedness to A is what?
I mean, in that case, it's just 0.5, right? Because it's their immediate offspring.
Yeah, exactly. So very high, but G's relatedness to B is this really small number. I don't know off the top of my head what it is. It's like probably no, I just want to calculate. It's going to bother me.
Is G's relatedness to B 0.5 to the power of 3, or is it still 0.5 to the power of 4?
Oh, yes, you're right. You're right. It's not this sum. You're right. It's 0.5 to the power of 3.
Okay, thank you.
Yeah, exactly. Okay, so that's just going to be like, what is it, 12.5% or 0.125, I think. Yeah. Okay, so G, so I'm going to do some more typing. G, like R for G to B is 0.5, R for G to A, oops, I got that wrong. Sorry. So, okay, so let's say that the benefit and cost of, like, let's say we're talking about G giving something away that, you know, the benefit and cost is the same. So all else being equal, we look at like that inequality of relatedness times benefit versus cost. So if we kind of ignore the benefit and cost because those things are equal, well, the total benefit is the little b times relatedness. And so anything that G could do, it's going to be more beneficial to do it for A than it will be for B, all else being equal.
And then would it be reasonable to say in this case that, say you were comparing the grandparents and A, that it would be more likely that G would want to care for B than A would ever want to care for B, right? Because G is slightly more closely related. Or is that, am I jumping to too many conclusions?
No,
now?
you're exactly right.
Okay.
Yeah.
Okay.
Yeah.
This makes much more sense now. I was very confused about how the lines meant relatedness, but I think I get the pattern now. So thank you.
Yeah, you're exactly right. And I don't want to confuse things, but one thing I'll say is that like in human generations, like by the time B is born, A here is probably really old. And, you know, G's probably not alive anymore. So it's a bit, we have to kind of pretend like, you know, pretend all else being equal, but in most cases, like it only benefits G to care for A if A is still able to reproduce themselves. So it's like just kind of putting a bit of realism on the question. The whole idea behind inclusive fitness is that you should be caring for an individual that's still going to themselves reproduce. So just caring for them alone doesn't give you inclusive fitness. It's the idea that they also then like create more offspring. So if
Right.
A is beyond their reproductive lifespan, then G should care for B. But I won't put a question on the test like that. Kind of focus on, you know, just assume all else being equal, who should G care the most for?
Okay, that makes sense.
Yeah.
I have a question. So since you added a G now, right? If you still wanted A to B, would the 0.5 change or no? Like would you add another 0.5 or would you just keep like
Oh, G, how related is A to B?
yeah, like does it
Well,
matter if
it that's this answer here. Oops. So this okay, so so even though I can't change the size of this or move it around, I don't know what maybe I have to go to select. There we go. Okay, sorry, I didn't know how to do that. Okay, so this is the answer of the relatedness of A to B, and the reason is there's two terms here because they share this ancestor, but they also share this one, and I didn't put a label on it, but this one is relevant to that calculation. Let's call it H.
okay.
Yeah, so you have to have one term in the sum for G and one term in the sum for H, and they're equivalent. You know, they both of those terms have 4 steps to get from A to B, and so
Okay, yeah.
yeah. So
Did
yeah,
you-
and so Charlotte's point stands. You know, if it comes down to like who should care for little B, G or A, by Hamilton's rule, G is more closely related to B, so G should care more. And if we look at like, oh, what about G or H? Who should care more for B, G or H? Well, maybe one of you can answer that. Out of G or H, which one of G or H is more closely related to B?
They would be the same relatedness, right?
Exactly. So all else being equal, we predict that G and H should be equally willing to care for B.
Okay, wait, this might not be related, actually. I don't think I'll ask because I think it's just gonna complicate. I was gonna ask about what if like G and H had different offspring as well, if that would affect anything, but I guess that doesn't change the relatedness to your
Well,
one shared
yeah.
offspring. So, but I think you'd care less if you had more offspring that was completely unrelated.
Well, yeah, no, but it's an excellent point because that is the real decision that is often being made. So, like, it's usually not all else being equal. Usually, it's like grandparents have many descendants to decide how to allocate their care to. And
Right.
so, yeah, so they're not like anything they invest in this grandparent might mean that they're not investing in this other, or sorry, grand offspring means they're not investing it in this other grand offspring. And so like optimality models can look at like a purely theoretical point of view, what's the best way for them to allocate their care? And then Hamilton's rule is part of how you determine that. So if all the grand offspring have the same relatedness to a given grandparent, maybe they're all equivalent in terms of Hamilton's rule, but then in a cost benefit model or an optimality model, you might also want to figure out like how likely are those different grand offspring to themselves reproduce. And it would be optimal for the grandparent to invest in the grand offspring that will have the most fitness itself later on.
Right. So I guess there's just other models that cover those types of things too.
Yeah, exactly. Yeah, the
Okay.
models can get more complicated, but we won't. That's trying to know, but we're not doing those models ourselves. Yeah.
Right. I don't know if I missed it because I joined a few minutes late, but did anyone go over or ask anything about game theory questions?
No, we have not.
I'm wondering if no one else wants to discuss this still, if it'd be possible to see like an example question of game theory, because that's the one of the other concepts. Like I'm a bit confused on how to go about answering that kind of question, I guess.
Absolutely. I figured that that would be a thing because I think those are hard to really do without us like working on a whiteboard or whatever. So I've been like worried that people don't get it and just don't, we haven't had a chance to check in about it. So
Like it's one of those things where it makes sense when I watch you answer it in the lecture, but then when it comes time to actually like start answering it myself, I'm like a bit confused as to where to even begin with it.
okay. So why don't, I think I made some practice problems. I was trying to find them. Practice problems. Oops. Yeah, okay. Okay, and I will say, yeah, it's confusing. And part of the tricky part is like making sure it's not hard. It's just like easy to make a mistake, especially if you haven't done it a ton of times. So you can see my screen now, right?
It's still on the relatedness tree for me, but
Oh,
I can see
okay.
it.
Okay, sorry. I thought I switched to sharing my desktop. Okay, but you can now see a PDF.
Yes.
Okay, perfect. All right. Okay, so like these matrices can appear in different formats. So what I've been trying to do is like color code the payoffs as to whether they pertain to the column player or the row player. So pay attention to like the coloration or the shading. I think there's a game theory question on the midterm that I used shading, like one of them is like gray and one of them is black or something. And hopefully you can all see, this orange, this lighter one in the rows is orange, and then the darker one here is sort of dark green. Okay, so what this means is that if player A is playing dove and player B is playing dove, they would end up with the same payoff. They would both come out with +1. If player A is playing hawk and player B is playing hawk, they'd come out with the same payoff. They both come out with 0, no gain or loss. If player A is playing hawk, the aggressive strategy, and player B is playing dove, then we're in this scenario here. And what that means is the player B gets a little bit of a benefit, but player A gets the bigger benefit. So the payoff is +0.5 to B, but +1.5 to A. And then we see that this is a symmetrical game because when we look at the kind of opposite scenario here, we see the same numbers, but flipped. So like all together, we can see that this is a symmetrical game. Okay, so that's what these matrices are telling us. Okay, so the first thing you have to be able to do is just say, is there an evolutionarily stable strategy? Okay, so to do that, just if it's a symmetrical game, you just pick a player. It doesn't matter which one. So let's just pick player A. And let's say what we want to answer is, if player B plays dove, what should player A do? So can you answer that? Somebody.
They should play hawk.
Correct. Okay, so if player B is playing dove, player A, the best strategy for A is hawk. If B plays hawk, then what should A do?
They should play dove in that case.
Exactly. So the answer is shown on my page, so it's not the best, but yeah, exactly. So if we have a different best move for A, depending on what B's doing, that means there is no ESS. It means that the best option, sorry, I'm getting some weird sound. I hope you guys are hearing me okay. But the best option for A depends. And so there's no one universal best.
Okay.
Okay, so
So
that,
if
oh yeah, go ahead.
if one player's strategy like best strategy depends on what the other player's strategy is, then there's not an ESS.
Correct.
And would it be possible for, is it possible that there be like a case where for player B, it doesn't matter what player A does, but then player A, it does matter what player B does? I guess that wouldn't be a symmetrical game though at that point, right?
Exactly. Yes, it's
Okay.
possible, but it would be an asymmetrical game.
And in that case, you wouldn't be using this method to find if there was an ESS?
Well, we'd ask the question separately for like the A type player and the B type player, because
Okay.
that was telling us there is an ESS for one of the player types, but not for the other.
Okay, so that's possible in an asymmetrical game?
Exactly.
Okay, perfect, thanks.
Exactly. So I forget what the other example is. So here's another one. Okay, so I'm like going to hide the answer, but it's not way on the bottom of my screen. Okay, so what about here? Is there a so again, let's look at player A. If B plays dove, what should player A do?
Play dove as well. Oh wait, what? Sorry, what was the
Hawk,
question?
right?
If B plays dove, what should A do?
Oh, play hawk in that case.
Exactly, because 3 is bigger than 2. And if B plays hawk, what should A do?
Play
In this
hawk.
case, they would still play hawk.
Exactly. So no matter what B does, A should play hawk. So there is an ESS, hawk.
Of Hawk. Oh,
Yeah.
So when it asks what the ESS is, you just give what play you would use?
Yeah.
Okay.
Now there just isn't one sometimes. But in this case, there is. And what will happen is that no matter what the starting frequencies are, the evolution would progress towards a population of hawks, of all hawks. Whereas if there is no ESS, the evolution or the evolutionary pathway will progress towards some balance of hawks and doves. And the exact balance will depend on the numbers in this table.
Right. And that second example you just showed, that was asymmetrical, right? Because for B, oh no, it wasn't. Sorry, I didn't see the 3. So for that is, oh sorry, there's background noise. Is it the same for player B? Now I just confused myself. Sorry,
Yes.
I didn't realize they were both 3 and 1. But yeah, it's the same. It's the same ESS for both in this case. Then
It is, and it's just
okay,
it's
perfect.
tricky because you have to like flip, like you have to just keep careful track. It's not hard, but it's tricky, right? So we could have asked the question in the flip way. We could have said, okay, let's be player B. If I'm player B and player A is playing dove, what should I B do? I should play hawk. And if I'm player B and player A is playing hawk, what should I player B do? I should play hawk. Yeah.
So in this
the
case,
arrow thing is really.
sorry, go ahead.
Does the arrow thing always work? Like if you just like I don't know, you showed it in the examples before. When you compare the numbers, then you go towards the highest number.
Yeah, it does always work. Like they're way more complicated scenarios than the ones we're looking at in class. Like there are games where there's 3 strategies. There are asymmetrical games with, more than 2 strategies and things like that. So, but for this class, you can answer that question of is there an ESS just by kind of looking at the table, and you can, like, using the arrows correctly, you can answer that question, that first
Okay.
question. Yeah.
In this game, is the ESS per player or is the ESS just like general, Like, would you state that as like, oh, for player A, it would be to play Hawk, or is it just like in this game, it is to play Hawk?
Because it's symmetrical, it just is Hawk.
Okay,
Yeah. So what a symmetrical game means is that like A and B are interchangeable. Like it doesn't
Right.
matter if A is me and B is you, or if A is you and B is me. The payoffs are the same.
So when it's symmetrical, the ESS applies to the entire game and like both players.
Correct.
But if it was asymmetrical, the ESS would only apply to the one specific player, potentially.
Or we have to consider each one
Right.
separately. Yeah.
Okay.
Or we'd have to kind of analyze each one separately. Yeah. Okay. So here's the trickier part, I think, is doing the calculation. Was that okay? Or
Well, if you could
Can you
run
go
through
over
that, that
it?
would be great.
yeah, I would love to go over it. So I want to come back to this one where there is an ESS. And I just want to say when there is an ESS, there's no calculation because it just means that the population will evolve to be all hawks in this case. So we don't need to do any further calculations. Okay, but if there is no ESS, then we can ask the question, what will the equilibrium frequency be? Because when there's no ESS, it means that like what the best strategy is depends on the frequencies in the population. And so we can figure out what those frequencies will be at equilibrium. Okay, and so this is where I feel like it's a bit trickier, but still it's not that hard. It's more about just not getting confused about the symbols. So, okay, so there's two different types of symbols that I'm using here. I'm using a set of symbols to represent the frequencies or the proportions in the population. And for that, I'm using like these little H's and little D's. And then I'm using big H's and big D's to represent the average payoffs. Okay, so I know that the proportions have to sum to 1 just by definition. So there's just this like relationship between little h and little d, where little h plus little d equals 1. So I'll just kind of put that aside. We'll use that later. And then what I do is I use the payoff matrix to write out the expected average fitness of each strategy. So we can write out the average fitness of D and the average fitness of H. And I kind of wrote out each equation, then I simplified it over here, but you don't have to do it that way. I could have written one equation here and then the other one here and then simplified each one below. But okay, so how do I get these? So I'm going to look at the orange player. And so I'm just going to say, okay, first I want to get the average fitness for playing Dove. So that's big D. And what it is I just go in and I get the payoffs for that strategy multiplied by the corresponding frequency of the opponent strategy. So the average payoff for playing Dove, big D, is this orange 1 multiplied by how probable it is that you would encounter another D. So that's little d. Little d is like the proportion in the population playing Dove. So 1 times little d plus 0.5 times little h. And and then the second equation, the average fitness of the Hawk strategy is just 1.5 times little d plus 0 times little h. Okay, so those are my equations. And then the rest of this is just like doing, a couple separate, like 2 equations with 2 unknowns, kind of simplifying and substituting. And so oh, go ahead.
Sorry, I just wanted to make sure I'm understanding it. So for the big D, which is like their likelihood of surviving, it's It's what the so when you're a dove and then you encounter another dove, but little d is the proportion of, so since you're both doves, that's one. And then since, is that what that means? Like, I'm a bit confused about.
Yes. Okay. What does it mean? Yeah. Okay. So this whole thing, big D is the average payoff to the dove strategy. And the average payoff to the dove strategy depends on how many other doves there are out there. Because as we saw, the dove strategy does pretty well when it's up against another dove, but not so well when it's up against a hawk. Okay, so the average payoff to being a dove is a function of the probability that you're going to come across another dove versus another hawk. Okay, so that's why the average payoff to dove is a function of these proportions, and these proportions tell you the probability that, like, if I'm just out there encountering opponents, if the whole world is other doves, then, you know, everybody I encounter is a dove. But if the world is 50-50, well, then this is 0.5 and this is 0.5, and half the time I encounter another dove, but half the time I encounter a hawk. If the whole world, yeah, so we don't know what those little numbers are, but that's what those symbols represent, is the you know, this is the payoff every time I encounter a dove times the probability that I encounter a little dove, and this is the payoff every time I encounter a hawk times the probability that I encounter a hawk.
Okay, I didn't realize that we were multiplying the payoff to the probability. That makes much more sense. I was confused because I was like, if D is the probability of us seeing it, then why is it also the payoff? But no, I see that we're multiplying by the payoff. So that makes much more sense. Sorry.
No problem. Yes. So totally. Yeah. So that helps like make sense of the steps that we're doing to know what we're trying to summarize here. So yeah, so big D, average payoff to playing dove, and it's a function of the proportions of the strategies out there in the population, multiplied by the payoff of facing off each one of those strategies. If you are a dove, so if you're a dove, you get a 1 every time you face off against another dove, and you get a 0.5 every time you face off against a hawk. And then the same thing pertains to this one. It's like the average payoff to playing hawk is the payoff a hawk gets when it faces a dove times the probability of encountering a dove. And then the payoff a hawk gets of facing a hawk, which is 0, times the probability, little h, of encountering a hawk. So once you get these, I assume you're okay with like the kind of simplifying and substitution.
Yes, that part makes sense.
Okay, cool. Yeah, and if anybody else is not, just let me know. Yeah, okay. Yeah, so then it's just kind of bookkeeping and substitution. So like we do some simplifying, but then we go back and we get this thing that we started with. I said we'd put this aside and use it later. Well, once we simplify these two things, we know at equilibrium, by definition at equilibrium, big D must equal big H. So we can set this equal to this. And I've already done the substitution, so I can express both of these things either in terms of little d or little h. And by the way, that's a good way to like check your work. Like you could answer this question by solving for little d. And then you could like do it again. If you want to check your work, you could do it again, but now like do it solving for little h and make sure you get like, you know, the answer that makes sense. That could be a way to kind of check your work. If you get and little d plus little h should add to 1. But if you end up getting like a different pair of answers each time, then one of the 2 times you made a mistake.
And then since this is symmetrical, you only have to do that calculation the one time, because
Correct.
no matter which way you do it, it's the same answer.
Yeah, exactly.
Okay.
Yeah.
If it wasn't the same, Oh, but you would only be calculating that for when it's, yeah. Oh no, but this is not ESS. Okay.
Yeah, so like, I don't think this PDF has an example of an asymmetrical game.
Right.
Um, if yeah, so I guess I would just say don't worry about that.
Okay.
Yeah.
Thank you.
At the bottom of the page, there's like graphs as well.
Oh yeah.
Are we supposed to know this as well? Or
Yeah, and I never showed this in class. So okay, so what these graphs show is just the equations of those lines. So like these are different scenarios, right? But these like these expressions
Mhm.
here that I'm waving my mouse around on, they can just be plotted as lines. So it's like the average or the average fitness. You know, if h equals 1.5d, that's a line with a intercept of 0 and a slope of 1.5.
Oh, okay.
So so these are just a graphical representation of those equations. And the point where like red is the average fitness of hawks and blue is the average fitness of doves. And if they cross, that's an equilibrium. And if they don't cross, what that's telling you is that like, so here, let's look at C. In C, the dove fitness is always higher than hawk fitness. So no matter what the population composition is, doves are always fitter. So that's telling you that dove is an ESS. Doves
Oh,
are,
okay.
yeah, like it's better off to be a dove no matter what the population composition is like.
Okay.
And here it's better off to be a hawk no matter what the population is like. So these are graphical representations of scenarios where there is an ESS. And then these are scenarios where there's not, and instead the population will evolve to reach that balancing point. And in this case, the balance point ends up being where it's half hawk, half dove. And this is an example of like a population that'll evolve to be like point, I don't know, 6.5, like 65% hawks or something like that. Yeah, I think I'm 66.
Mhm.
Yeah. Yeah, I didn't like cover this in lecture, so I think it's good to know. It kind of reinforces what we're doing, but I don't have any midterm questions that are like this.
In the first graph there, A, since like you're equally well off either way, that would be a scenario where there would be no ESS, right? Because you're equally good playing hawk or dove. Or am I completely misinterpreting that?
You're right that there's no ESS, but okay, so let's say the population composition is 10% hawks. So if little h is 10% or 0.1, what are you better off playing?
You'd be better off at hawk, right? Because that's got the higher fitness.
Exactly.
Okay.
So what will happen is like hawks are doing better, more hawks will reproduce more, and the population will start to move toward that equilibrium point.
Okay.
We'll start to get more and more hawks in the population. Whereas if we start off with 90% hawks, then it's better to play dove. The doves are having greater fitness. So then we're gonna start getting more doves, which means fewer hawks, and we're gonna start to move towards that equilibrium.
Okay. So you're only, the two strategies are only equal when they're being used equally, I guess. Is that right?
Well, there's a difference between the proportion of the two strategies being 50-50 and the two strategies having equal fitness. In this scenario, those two things happen to be equal fitness happens to happen at 50-50.
Right. And then in B, it happens at
Yeah, exactly.
70. Okay,
Yeah.
cool.
Yeah, and B equal fitness happens when there's 66% hawks and 34% dove.
Okay, cool. Thank you.
So no matter where you start, your population will evolve towards there being 66% hawks in this, with this particular, the payoff matrix that leads to this set of equations. That's what will happen. Yeah. Yeah, those are good questions. Okay, other questions?
I have one more question.
Okay.
Just regarding inclusive fitness.
Sure.
So with that example of the subordinate turkey and then the dominant turkey, that would be an example of inclusive fitness, because even though the subordinate is not mating, it kind of still gets its genes passed along in some ways. Is that right?
Exactly. Right. Okay, so I'm just going to that slide. Okay, so the idea is that the dominant turkey is going to reproduce,
Mhm.
and the subordinate turkey, so people study this and kind of measured the relationships. They were often like brothers, but sometimes they were a little bit more distant than brothers. But the average relatedness between the male coalition partners was 0.42. So that's like, you know, on a lot of them were 0.5, but some of them were a bit less. So they were on average quite related. And then they would calculate the different kind of fitness benefits of the dominant, you know, like what was the average number of offspring that a dominant male would get, and what was the average number of offspring that a male with no coalition partner would get, and so on. And so they could work out like the benefit of being a subordinate, because the benefit of being a subordinate would be your relatedness to your partner, your dominant partner, times the dominant partner's offspring count minus the cost of your own offspring count. So how many of your own offspring are you not having because you're playing subordinate to somebody else? And so, yeah. So if the dominant wasn't having any offspring, then you wouldn't be getting any benefit at all of being the subordinate. So it all relies on the fact that the dominant male is having a lot of offspring here.
All right. And since you mentioned, like, if the dominant one wasn't having any offspring, would that be an example of Hamilton's rule not being satisfied, like less than 0?
Exactly. Yeah. And
Okay.
like there's lots of examples in nature where it's not, right? And so I'm sure there are cases where the two coalition partners, like the dominant male doesn't mate at all. And this is all just on average. But it
Okay.
doesn't mean that every single pair of turkeys satisfies the equation. It's just that on average, it is satisfied for this in this study.
Okay.
Yeah, but like,
Thank you.
yeah, good question. Anything else?
Yeah, I guess we've gone over the time that you offered. So thank you for taking time to answer all our questions.
Yeah, of course. I hate that we have not had time to do it in the classroom. It really bugs me. So yeah, I appreciate that these things with like the game theory stuff and the relatedness stuff, it's just so much easier to get when you can like do it in person.
Absolutely. Forces you to actually actively do it too, which is nice because it's easy to just get passive when you're watching lectures. So
Yeah. Yeah. Okay.
Thank you so much.
Thank you so much. Have a good
thank
night.
you.
You too. Good night.